Okay, so let's continue our discussion related to sinusoidal steady-state analysis. And we had looked at the concept of phasor for analysis of these circuits. So the basic idea was that if I have a linear system and I would like to understand it, I would like to characterize it. A linear system like, for example, consisting of, let's say, a very simple system consisting of one resistor and a capacitor. Then what we said was you can excite it with a sinusoidal signal. And so we do that here. And if you study the response to the sinusoidal signal in steady state, meaning that the sinusoidal signal has been applied for a long time, and because it's a linear system, so the output is proportional to the input, so it doesn't really matter if you want to understand the system what the value of ES is. So for convenience, one is taken as 1. And so you look at what the output voltage is, which will also be a sinusoid, we said. We'll have some amplitude and some phase here. And so you study the amplitude and the phase as a function of the frequency, right? And the amplitude and the phase of the output, let's say, as a function of frequency, that completely characterize the linear system that is there here, right? So we said if you take R and C, excite it with a sinusoidal voltage, the output will also be a sinusoidal. Look at the magnitude of the output voltage here. So the magnitude as a function of frequency, and you look at the phase. The output will have some magnitude and phase, and you look at the phase here as a function of frequency. So these are two very useful information which tells us how the system behaves. So in this case, we had seen in the last lecture, we can understand that the whole circuit is like a low pass filter. It allows lower frequencies to pass through as they are, but higher frequencies are attenuated. They are attenuated severely. And also you can see here that the phase undergoes a change at higher frequency. The phase is 90 degree, minus 90 degree compared to the input here. The input is being taken as 0 phase here. All right, so let's, so the basic idea that we had discussed in the last lecture was that if you, and what we've been discussing just now is that if you take a linear system, excite it with a sinusoidal signal, and look at the response of the output here, and response in terms of the amplitude and the phase. And we had said that if you want to characterize, if you want to analyze a system using this excitation, you can do that in a much more convenient manner by looking at a signal which is a exponential signal a e to the power j theta e to the power j omega t. And the idea behind this was that when an exponential signal e to the power j omega t goes through a linear system, every term has e to the power j omega t also. So the output is also some y0 into e to the power j omega t. And if you're looking for y1, you can obtain it by taking the real value of this, by real value of this particular one. And because e to the power j omega t is common in every term, every current and voltage has e to the power j omega t in it. So you can actually take it out and analyze the system only in terms of the amplitude and the phase part here, a e to the power j theta here, and only the amplitude and the phase part embodied in y0 here. So you analyze the system only in these terms. We understand that there is a e to the power j omega term here, and we understand there'll be a e to the power j omega term, but we add that up later on when we want the full signal in the time domain. But in the meantime, in the interim time, is much simpler because e to the power j omega t is everywhere. It's much simpler to just consider the pre-exponential part here, which is a complex number here. And similarly, the output is a complex number here. So analyzing circuits in terms of, and this is what we said are called phasors. All right, so let's continue with that. So if you want to analyze a circuit only in terms of these phasor inputs, phasor voltages and phasor currents, and please understand again, what do we mean by phasor? Phasor is the pre-exponential part here. So phasor part multiplied by e to the power j omega t. And if you take the real of it, that gives you the actual signal that is there. Okay. All right. So if you want to analyze, then what we can do is every component that is there in my linear system, I can describe it in terms of a phasor relationship. Okay. So phasor relationship. So if I take a capacitor or an inductor or a resistor, the relationship between phasor current and phasor voltage will be a impedance. And in general, we'll see that impedance can be a complex impedance. So let's calculate that relationship for a few common components. So we take an inductor here, and we know the inductors, let's say the current through the inductor IL is Im e to the power j omega t plus theta here. Remember that the actual current would be real part of this, okay? So we are just taking Im into e to the power j omega t plus theta. In terms of phasors, we don't take e to the power j omega t. We do not consider it explicitly. It's there in the background, and we only simply represent IL in terms of Im and angle theta, which is nothing but Im e to the power j theta here, right? It's a short form of representation. This is what we are calling as the phasor representation of inductor current. So VL will be equal to L dIL by dt, right? So we take IL here, plug it here, and we get j omega L into Im e to the power j omega t plus theta. So again, e to the power j omega t, we keep it in the background, so we can represent it in the form of a phasor. So the phasor inductor voltage is equal to j omega L. We keep it as it is, Im, and e to the power j theta, we represent it as angle of theta here, right? So this j part is there here, and this j part here, we can combine it with this angle here, and j part also, note that can be written as angle 90, because we can write j as e to the power j theta, and theta is 90. So when you take cos theta plus j sine 90, you'll get a j part there here. So we can write j as angle 90 here. And we can see here then, you know, the two angles, you can combine them together. So it will be 90 plus theta. So we can see that the current through the inductor lags the voltage by 90 degree, or the other way, we can say that the voltage across the inductor leads the current by 90 degree. And that's understandable because we know that it takes time for the current to build up in an inductor, right? The current through the inductor does not change instantaneously. It takes time for the current to reach its final state, and so there's a delay, and that delay shows up in the fact that the current through the inductor will lag the voltage applied by 90 degrees here. So we can write this expression as VL equal to j omega L, again back into j omega L, multiplied by the phasor current here. Note Im angle theta is nothing but phasor current here, and this is VL here. So we have obtained for an inductor the relationship between the phasor voltage across it and the phasor current flowing through it, and this is the relationship here. And we can write it as VL equal to ZL times IL, where ZL is what we call as the impedance of the inductor here, which is equal to j omega L here. So this is also like an Ohm's law, right? There's nothing, current voltage being proportional to current with a constant proportionality constant is like an Ohm's law. But this relationship is between the phasor voltage and the phasor current, right? So whenever we are analyzing the circuit in terms of phasors, and we see an inductor somewhere in the circuit, we are going to take the inductor and replace it by this value here, j omega L, because that gives us the relationship between phasor voltage and phasor current through it. Now, similarly, we can derive a similar relationship for a capacitor. So capacitor, we know I equal to C dV by dt. And let's take the voltage across the capacitor as Vm e to the power j omega t plus theta here. So all signals are sinusoidal. So this is a general form of a signal, let's say across the capacitor, voltage across the capacitor, which we represent as Vm angle theta. All right, so let's take this expression, put it here. We get Ic equal to j omega Cm e to the power j omega t plus theta here. And we can represent, of course, in a phasor form as j omega c Vm angle theta here. And j is nothing but angle 90, so we can combine them together into angle theta plus 90, and therefore we know that in a capacitor, current leads the voltage by 90 degree, or voltage lags the current by 90 degree, and that's understandable because we know that charge across a capacitor takes some time to build up, and therefore the voltage also takes some time to build up, and therefore the voltage lags. All right, there's a delay and there's a lag, and that is by 90 degrees when we apply sinusoidal signals here. So this is a well-known relationship. And coming back again, I see this relationship j omega c Vm angle theta. So this, let's write it down here. And Vm angle theta is nothing but Vc, right? The voltage across the capacitor. So again, we obtain a relationship. We can rewrite this relationship as Vc equal to Ic into Zc here, like a Ohm's law, with the impedance of the capacitor being given by 1 over j omega c, or minus j by omega c. So the idea is, again, the phasor relationship between a voltage and a current across a capacitor is related through an Ohm's law. Ohm's law like a relationship here, where the capacitor is replaced by an impedance which is equal to 1 by j omega c. So you can see the advantage of doing phasor analysis is that a derivative the relationship between current and voltage is a derivative, the derivative is now gone and is replaced by the relationship between voltage and current is like an Ohm's law, is replaced by a complex number here, right? So the replacement of a derivative or an integral by a complex number is the advantage that we get in phasor analysis. Makes the whole analysis simpler, as we'll see. So that's the capacitor. So everywhere, anywhere in the circuit, if you're doing sinusoidal steady state analysis using the concept of phasors, wherever you see a capacitor, replace it by a number, a complex number 1 over j omega c. So that denotes the relationship between voltage and current across a capacitor. For a resistor, it's even simpler. If I have VR equal to Vm cos omega t plus theta here, voltage across the resistor, current is simply Vm by R. And therefore, if you write VR equal to Vm angle theta, then IR equal to Vm by R angle theta here. So resistor basically stays a resistor. There's no change. So whether you're doing a phasor analysis or normal analysis, IR equal to VR by R, the relationship between the phasor current and the phasor voltage is nothing but the resistance itself. So resistors stay as they are in the circuit. All right, so let's apply this to some very simple example here. So let's say we are given a circuit, an inductor excited by a sinusoidal source, and we want to know what is the current flowing through it. And let's say we are given the voltage here. Voltage is 2 cos 200t plus some phase 45 degrees. So the first thing we note is that the moment you're given a sinusoidal signal, the first thing you should do is identify the angular frequency omega, which is 200 here. And therefore, in the phasor form, the signal can be represented as 2 angle 45 here, right? So that is there here. And the voltage across the inductor, so we have only one inductor. So VL will be nothing but equal to IL into j omega L. So that's the relationship between phasor voltage and phasor current. So inductor current, phasor inductor current can be obtained as IL equal to VL by j omega L. So that will be equal to 2 angle 45, fine, divided by J20. J20, if you put omega equal to 200 multiplied by 0.1, so that gives us 20. So J20 is the impedance of the inductor here. So J20, we can write it as 20 angle 90 here. And we divide the amplitudes and we subtract out the angles and we get 0.1 angle minus 45. Now you want, so this is the phasor representation of the current. If you want the actual value of the current flowing through it, well, the actual value of the current would be this 0.1 comes as amplitude. Cos 200t, we said e to the power j omega t, or omega t is there everywhere. So 200 cos 200t is there. Just add the phase here, minus 45, and you get the final value of the current. Right. So this is an intermediate phasor analysis we do because it's much simpler to do algebra in terms of multiplication or addition or subtraction rather than look at derivatives and integrals. Okay, so the basic idea of phasor analysis is if you want to take a circuit that is given to you, transform it into a phasor circuit. And the transformation involves convert the voltage into a phasor form, convert all the elements into the phasor form here. Do the analysis, get the value that you're looking for, and then after that transform it back into the time domain if you're interested. Okay. All right, so let's look at another example with two elements here. So we have this inductor and a resistor, and we are given this voltage again, 200t plus 45 here. So omega is 200, and the inductor impedance then is j omega L, right? So we get a phasor circuit. So from an original circuit, determine a phasor circuit. So the phasor circuit is replace it by 2 angle 45, replace it by an impedance J20, and resistor stays as resistor here 50. Now after that, note that the circuit is like the regular circuits that we handled before, consisting of resistors and dependent sources. The only thing is some of the elements have complex values here. So these two are in series, we can combine them up together. The concept of series, parallel, all those concepts are valid here also. So we can combine them together, write it as one equivalent impedance 50 plus J20 ohms here. We know the input here. So we can calculate what the current flowing through my system will be equal to 2 angle 45 divided by 50 plus J20 here. Now 50 plus J20 is a representation of complex number in rectangular form. Convert it into polar form here, or phasor form here, 53.85 angle 21.8 here, then divide the amplitudes, subtract the angles, and you get this form here, I equal to here. And then of course convert it back into your time domain. Keep the amplitude as it is, 0.037, cos omega t will be there like before, and add the phase here, 23.2, and you get the answer here. Okay. All right. So if you're looking for so we found out what is the current flowing through the system. Suppose you wanted to know what is the voltage drop across the resistor. Okay. So voltage drop across the resistor would be, the concept of voltage division is valid. All those things are valid here. So Vs is 2 angle 45 is the original voltage here, and it will divide between these two. And so the voltage division was, if you're looking for voltage drop across the 50 ohms, so it would be 50 divided by the net impedance, 50 plus J20 here. Okay, so concept of voltage or current division, all those things that we have studied, they're all valid. We have a linear circuit. The only thing is we are talking in terms of phasors, and the relationship between the phasor current and the phasor voltage is all linear relationship. So all those things that we studied, they're all valid. Thevenin's and Norton's equivalent circuit, we can do all of that, except that now note that this would be a phasor voltage and this would be some complex impedance. In general, it would be made up of resistors, capacitors, inductors. All of them have capacitors and inductors have a imaginary component. So in general, this would be a complex impedance. Similarly, Norton's current would also be a phasor current, and there would be a complex impedance here, Norton's impedance, which is nothing but same as the Thevenin's impedance here. So all those concepts are valid, all those things can be applied, and that makes the analysis of sinusoidal circuits in steady state similar to analysis of circuits that we did under DC voltages and currents. The only difficulty is that we have to handle complex numbers, and it involves a little bit of more calculation when you handle complex numbers here. All right, coming back to, so we've seen voltages and currents, how to calculate that. Let's look at power dissipation. So we know that if I take a voltage source and I connect it to a resistor, the power that is there in the resistor is V squared by R. So Vt squared by R here. And most of the time we are not interested in what is the instantaneous value of power. What we want to know is what is the average power dissipated. So when we talk about average, we take this is let's say a continuous signal, we take an average in the form of 1 over T, 0 to T, V squared R by R times dt here. We do the averaging by performing this integral. Well, a little bit of background on average. If you have a number, let's say a variable which can take values x1, x2, x3 to xn, and you want to find out average, all of you know, and if these values are discrete, all of you know that you take the average by summing up all these things and divide it by total number of variables here. That's how you take the average. If it's continuous, the same thing is if x were continuous, then its average over a certain time period t1 would be, integral is nothing but summation, and then divided over that time interval 1 over t1 will give you the average. So there's a direct parallel to this here, right? So here it's a discrete variable, here is a continuous variable, so that's how you take the average. And for periodic signals, t1 makes sense that you take it as the time period, because that will give you the average over a time period, which is nothing but average over multiple cycles also. So for a periodic signal, if you want to know what is the average of a certain quantity, take 1 over t, one time period, 0 to t, xt dt, and that will give it to you. Okay, so let's come back to our power dissipation. So power dissipation, we are looking at a circuit, a resistor across which a sinusoidal voltage or a sinusoidal current is there, and we want to know how much is the power dissipated across it. So it would be, power would be 1 over v squared by r, and averaged over the time period, 0 to t, 1 over t, where t is the time period here. Now, normally we would like to express, we are familiar with this, we would like to express power like P equal to V squared by R, just like when we had a DC voltage across it. We represented power was as V squared by R or I squared times R. So we would like to take this particular one and represent it in this form. So we could do it like this here, P average equal to, note that we want a square term divided by R, so we could take, so P average is then can be written in this particular form. And we can write this quantity as square root 1 over t, 0 to t, v square t dt, whole thing square. We can write it as VRMS here. VRMS is 1 over t integral of over the time period, square of the voltage dt here. And RMS is nothing but root mean square. So it makes sense why we are calling it root mean square. We are taking a root. And we are taking a root of the mean or the average of the square of the quantity here, right? 1 over t integral 0 to t is nothing but averaging operation. And we are taking an average of the square here. So that's why this whole quantity is called root mean square here. So the power then can be written as VRMS square by R here. Now the thing about this is that this is a very general definition or general representation of power dissipated in a resistor when we have any periodic signal. It need not be sinusoid right now, because 1 over t, 0 to t, v square t, there's no, right now we have not been specific about what that time period is or what the periodic waveform is. So in general, power dissipated across a resistor would be VRMS square by R, and VRMS is RMS voltage, root mean square voltages. This is how you find. You take the average of the square of the voltage over a time period here, right? And take the square root of it, and that will give you the RMS power here. So this is true for any periodic waveform. Let's apply it to a sinusoid. So VRMS is, so our signal is Vt is Vm cos omega t plus theta here. So you plug it here. And of course, it's a simple trigonometry, simple algebra here. So we'll not go through that. You can verify. Then that VRMS is nothing but equal to the amplitude divided by square root 2. And therefore, the power, so VRMS of a sinusoidal signal, of any sinusoidal signal, will be the amplitude divided by square root 2 will give you the RMS value here. So the power dissipated when we apply a sinusoidal voltage across a resistor would be, P average would be V square RMS by R, and RMS value is Vm by square root 2, and therefore power is Vm square by 2R, right? So this, in this particular form, when you write VRMS square by R, this is just like we handled it in a DC case where the power dissipated across the resistor was V DC square by R. So similarly for a sinusoidal case also, it is V square by R, but you have to take the RMS value. You don't take the direct value here, the magnitude or the peak value here, but you take the RMS value, which is nothing but the peak value divided by square root 2 here. Okay. Similarly, you could do it, you could write power dissipated in terms of voltage. You can write it in terms of current. So in terms of current, to do it, RMS current would be Im by square root 2, and IRMS will be defined in a similar manner here. You take the average of the square of the current and you take the square root of it. So that gives you the RMS current here. And P average is nothing but Im square R divided by, divided by 2 or multiplied by 0.5 here. So same representation, except note that the average power has a factor of half here because of the nature of the sinusoids. Different periodic signals will have, a different factor there, which comes about by taking the RMS value of that periodic waveform. What about the power dissipated in an inductor? Okay, so Vt equal to Vm cos omega t, and It, if we take calculate the current, we know V equal to L di by dt, so It is Im sin omega t here, let's say, and power will be Vt into It, instantaneous power, Vm into Im cos omega times sin omega, and this, we can write it in this form, sin omega cos omega, you can combine them, sin 2 omega t in this form here, and so this is equal to so much, and basically it's a sine. And so when you take an average of a sinusoidal, of a sine term, the average is 0. You can actually you can do the averaging by yourself. And the other one is there's an equal area here, there's an equal negative area here, and positive negative will cancel each other. And so average power dissipated in an inductor is 0. Inductor doesn't dissipate power. It can store power, it can release the power back, but it doesn't dissipate power here, right? P average is 0. Same thing, we can do it with a capacitor. Capacitor, let's say Vt is Vm cos omega t, It will be equal to minus Im sin omega t, some Im there, which is related to capacitance value. Instantaneous power is here. You can write it in this form, Vm Im 2 sin 2 omega t here. And that average is also 0. Average of a sinusoid is 0 over a time period. So average power absorbed by a capacitor is also 0. So it's only in a circuit, it's only the resistor which can dissipate power. Inductors and capacitors, they will not absorb any, they'll not dissipate any power. Okay, average power. Well, we can have a general case here. Suppose there's a signal Vt equal to Vm cos omega t, and let's say the current is It equal to Im cos omega t minus theta. As an example, let's say we have a circuit like this, and now we have a complex, let's say, impedance. So complex impedance with a magnitude and some angle theta. If we apply Vm angle theta here as a phasor input, the current is going to be, because this angle theta here, the current will be angle minus theta here. So that's what we are representing it. So this is Vt equal to Vm cos omega t. The phasor representation is Vm angle 0. It is Im cos omega t minus theta. The phasor representation is here. So what is the power dissipated in this particular element, or what is the power, which is the same thing as what is the power drawn from this particular supply here. So average power will be again 1 over t, Vt into It dt here, 0 to t. And I'll not go into the details here. Well, you can easily do the algebra here, and it will come out to be V power can be written as V RMS, I RMS cos theta. And so we had already seen how VRMS and IRMS comes into picture because of the averaging of the square part there. The RMS values come into picture here. So this is a more general representation. Multiply these together and show that this can be written as VRMS. VRMS would be Vm by square root 2. IRMS will be Im by square root 2. And then cos theta is there. So this term here, cos theta, is what we call as the power factor. So the relationship between Vt and It, there's a phase relationship between Vt and It here. You can see that the phase difference is theta, and cos of that phase difference is what we call as power factor. So the power dissipated in this particular element is Vrms into Irms into cos theta here. For a resistor, if we had done this for a resistor, we saw power is nothing but Vrms into Irms, or Irms equal to Vrms by R here, right? So for a resistor, power factor is 1, theta is 0, while for an inductor or a capacitor, the power angle, the theta is 90, and therefore power comes out to be 0 here. Okay, so that's a general relationship between general expression for the power dissipated in an element is equal to the voltage, RMS voltage across it, the RMS current flowing through across it, and the power factor, which is nothing but cos of the phase difference between voltage and current. So a general representation through which you can get the results for a capacitor or an inductor or a resistor or any complex impedance that is there. So just like we had the concept of maximum power transfer in the case of DC, where we had derived in an earlier lecture, we had shown that if Vs and R are fixed, then the maximum power dissipated in RL, the maximum power that can be delivered to the load, happens when you choose RL equal to R. So now when we have a sinusoidal circuit and we have all these complex, we have resistors and capacitors and inductors, the question is again, what kind of a load should I attach so that I get maximum power dissipated in the load here, right? So now we have a general case where we have Vs, which is a phasor voltage, and we have some impedance in my circuit. Note that any circuit that I'm talking about, I can represent it in the form of a Thevenin's voltage and some Thevenin's impedance. And the issue is, so this part of the circuit is fixed. Vs is fixed and Z is fixed. The question that we are asking is, what value of ZL should I attach here so that I get maximum power dissipated in this particular quantity here? Okay, so Z, Thevenin's impedance in general will have some real part and some imaginary part, R plus Jx. Let ZL also be some real part and an imaginary part, JXL. So the current that flows into my load will be equal to current flowing into the load will be Vs, the phasor voltage, divided by the net impedance R plus RL plus Jx plus XL here. And the net power dissipated in ZL is going to be the magnitude part here, Vs square, the whole, basically the magnitude of IL square multiplied by RL divided by 2 here. So there should be a factor of 2 which is missing here. So that should be there. Or one could say that Vs given is let's say in this RMS format here. As an RMS value, if it is given, then it's fine. Otherwise, if it's the peak value here, then we have to put a 2 here. So for maximum power, note that when we look at the power dissipated here and we have this quantity here. So for maximum load power, we want PL to be maximized. So the first thing we can do is we can cancel. Note that we have to minimize the denominator. So the first thing that we can do is we can make choose XL, the imaginary part of the load impedance, to be equal and opposite to the imaginary part of the Thevenin's impedance here, JX here. So XL equal to minus X. So this term goes away. And we are left with PL equal to Vs square by R plus RL square times RL. Now this is similar to the DC case. Just like the DC case, we have the same thing here. And you can easily see that this term is maximized when we choose RL equal to R. Okay, so we have a condition for maximum power transfer that you should choose RL, which is equal to R, and you should choose the imaginary part JXL as conjugate of this particular part, as minus JX here, which is same as saying that you should choose the load impedance ZL as the complex conjugate of the Thevenin's impedance here. So if you do that, then you will get maximum power transfer to the load here, right? So that's a generalized maximum power transfer result when we have a concept of phasor here. When we have inductors and capacitors in the circuit, then we have this general result that choose ZL to be complex conjugate of the Thevenin's impedance here. All right, so let's wind up our discussion with one more example. So we are given a circuit like this, which consists of 2 inductors, a capacitor, and a resistor. And well, determine all you can about the given circuit. There are many things you can determine. So in the limited time that we'll have, let's determine a few things. All you can about this circuit means you can find out all the voltages, all the currents, all the power that is dissipated there, and all those things that are there here. But let's find out a few things. So in order to analyze this circuit using the concept of phasor, the first thing you start with is you have to obtain the phasor circuit. Transform this circuit, which is in terms of actual values of components, transform it into a phasor circuit where all the elements have been replaced by their complex impedance values here. To do that, the first step is identify the frequency here. So frequency omega is 50 here. So that would allow us to calculate what is the value of the inductance here. So first thing is also they represent the input as 50 angle 0 here. A resistor stays as a resistor, so that's straightforward. Now we replace the inductor. Inductor is j omega L. We know omega, we know L, so that's J5. So both of them are the same, so J5 here. Capacitor is minus J by omega C. So omega is there, C is there, so we can replace the capacitor minus J20. So that's the phasor circuit for the problem that is given here, right? So now we have, it's like a normal, any of the circuits that we have done before, except that we have complex numbers also in a circuit. So let's say I'm interested in what is the net current flowing through here. Let's calculate what is the amount of current drawn from the supply here, I. So to do that, what we'll do is we'll find out the net impedance of this particular part here. So note that these two are in series, then they are in parallel, and then they're in series. So that's exactly what we have done. Z equal to the two of them minus J20 plus J5 gives us minus J15. That's in parallel with 100 and in series with J5 here. So we do that. There's a bit of algebra here. And if my calculations are correct, it should come out to be 2.2 minus J 9.67. So that's the value of Z here. So the current flowing would be the phasor voltage 50 angle 0 divided by Z. And if we do that correctly, this is what it comes out, 1.12 times J 4.96, which can be represented in a phasor form 5 angle 77.2. All right, at this stage, we found out how much is the current drawn. Suppose I want to know how much is the power drawn from the supply. So power drawn from the supply would be the phasor voltage in RMS form, so 50 by square root 2. The value of the RMS current, which is 5 by square root 2, and the angle between this current and this voltage here. That's the power that is being supplied by this particular source. And so the angle is this angle 77.2, and we take cos of that, and that's the power factor. So we multiply them all together, and the power drawn from the generated by the, or power supplied by the source is 27.97 watts here. And where will this power be dissipated? Well, if the inductor cannot absorb power, the capacitor cannot absorb, this cannot absorb. So all this power must be dissipated across 100 ohms. So we can check that. We can check that by calculating how much is the voltage across 100 ohm resistor. So if I want to find out how much is the voltage across the 100 ohm resistor, we know that this current I flows through a parallel combination of 100 ohms and these two elements here. So I can calculate what the voltage across R1 is. VR1 is I times 100 parallel minus J15. That's the combination of these two. And that, if you do it properly, is 74.8 angle minus 4.3. So that's the value of the voltage across the resistor here. And what will be the power dissipated in the resistor? Well, power dissipated in the resistor, current and voltages are in phase. So it's nothing but RMS value of this here, 74.8 whole square divided by 2 divided by R1. So that comes out to be 27.97 watts. So exactly matches with this one. So all the power that is drawn from the supply, this power it can go nowhere else except this particular resistor, and that's what it checks out. So 27.97 watts. All right, so with the approach that we have now, we can take any complex circuit consisting of resistors, capacitors, inductors, dependent sources, and we can analyze them using the concept of phasors. And the procedure is that first transform the given circuit into a phasor circuit. And to do that, what you need to do is identify the frequency and then convert all the elements into their complex impedances. After that, the analysis is pretty much the same that we have been doing, except that you have to handle complex numbers. And when you're looking at power, so power will be voltage into current multiplied by the phase difference between voltage and current, which we call as the power factor. All right, so let's stop here.